Hi everyone, today I am presenting our work Recurrent Multigraph Integrator Network for predicting the evolution of population-driven brain connectivity templates. This work has been done at the Basira Lab by myself, Oytun Demirbilek, and supervised by Dr. Islam Rekik. Let's start with the Connectional Brain Template, in short CBT, and what it means. First, a CBT should satisfy two substantial criteria: well-centeredness and discriminativeness. Let us tackle a subject in a brain network population. A subject has multiple morphological measures, namely views, producing multiple graphs. Thereby, each subject is a multigraph, together a multigraph population. A CBT should be in the center of this population by minimizing the distances to each view of each subject. We represent CBT and each view of the subject as symmetric adjacency matrices. After we stack these adjacency matrices of views, a subject is represented by a tensor. In terms of discriminativeness, let us have two different populations with different brain states. Let's say A and B. After we integrate each population into a CBT, we can compare overall differences and easily determine the distinctive connectivities or regions. However, our main problem is not only to integrate but forecast. Let us have a subject S on a specific time point t1. Since the brain connectivities are dynamic, it might change over time, particularly in certain diseases such as Alzheimer's. When we have multiple time points for each subject in a population, we define this as longitudinal brain multigraph population, and we can integrate them into longitudinal CBTs using an end-to-end model. But what if a model would forecast CBTs without the need of future time points? We could predict and compare the changes at population level. Therefore, we design a predictive integrator that forecasts CBTs at future time points. Currently, DGM presents the state-of-the-art method in the CBT estimation task. It generalizes to multigraphs and exploits geometric deep learning layers, but it is an end-to-end model that is not customized to learn longitudinal dependencies and forecast. To address these limitations, we propose Recurrent Multigraph Integrator Network, in short ReMI-Net, that generalizes to longitudinal and multi-view data, uses novel graph convolutional layers, and pioneers the longitudinal CBT forecast and evaluation. Our model uses the population subjects only at the baseline time point and is designed with novel graph convolutional cells and a normalization layer. A subject S in the population is first normalized since its views largely differ in terms of value range. Next, we create a zero matrix that represents the weights to learn for each node, which we call hidden state node embeddings. This means each node has a learnable embedded vector that changes over time. A normalized subject tensor feeds all the convolutional cells, and each cell tracks the longitudinal changes by learning the hidden embeddings for the consecutive time point. Now we will need to obtain a symmetric matrix from these learned weights. To make this operation easily differentiable, we perform several tensor operations. First, we replicate the learned weights nr times and transpose the last two dimensions. Second, we take element-wise absolute differences between these two tensors and sum along the second dimension. We repeat this until we generate a CBT for all the training subjects. After training is complete, we take the median of each connectivity to refine the most centered population CBT. Now, I explain how these convolutional blocks work. Each convolutional block uses two information: the subject tensor at the baseline and the current hidden state node embedding matrix time t. This block also includes two RNN cells and a linear layer. First, we select the hidden vectors for node I and its neighbor j. Then, take the connectivity weights between node I and its neighbor j. Next, Hj is learned by the first RNN cell and Hi is learned by the second RNN cell, both using the same edge information between the two nodes. Next, we combine the outputs of these RNN cells by element-wise multiplication to create an overall message. We repeat this operation until we create messages for all neighbors of node I. To embed messages at node level, we calculate the element-wise average of these messages to node I. We also pass Hi to an additional linear layer for learning node-specific features. Then we add it to the overall message vector. This embedded vector is created for all nodes in a multigraph, and the combination of these is the hidden state node embeddings at the next time point, t plus 1. We compare our results by measuring the average Frobenius distance between the population subjects and the estimated CBT for both datasets, right and left hemispheres separately. We evaluate our model by selecting the best model across epochs with an early stopping strategy, since the model parameters and the convergence epochs are different. Note that DGN needs the information at time point 2, whereas ReMI-Net uses only the baseline time point, which is 1. We report the overlap rate between regions picked by CBT-based methods and the supervised feature selection method. Our proposed model is significantly more reproducible in discriminability than net norm for both hemispheres and than DGN for the right hemisphere. Thank you for listening.